So thank you very much, and I hope you enjoy the presentation.
All right, thanks. Yeah, by the book. Okay, so today I'm going to be talking about not about slavery, but about a methodological paper that project that I've been working on with Anton Streznev, who was a graduate student here in the department, graduated last year now, a postdoc at University of Pennsylvania. So the basic idea behind this paper is that it fits into a lot of my methodological research that focuses on trying to estimate a particular quantity of interest, which is what I'm going to loosely right now refer to as a direct effect. I'll be more precise about what I mean in a second. But generally, a direct effect, again, loosely, is just the effect of some treatment that's not due to some particular downstream cause. Right, so we're going to think about kind of fixing some downstream cause and then just varying treatment to see, is there a direct effect of treatment net this post-treatment thing. So why do we care about these kinds of direct effects? So they come up in a lot of different settings. In particular, the direct effects are the cornerstone of what we might of kind of causal mediation analysis and thinking about things like indirect and direct effects. Kind of, if you take a broader view, like I tend to do, these kinds of direct effects can help us evaluate causal mechanisms. And theoretically, social sciences might come up with theories that predict certain kinds of direct effects and not others, and we can use evaluate these direct effects to kind of evaluate these causal mechanisms. And another kind of broad area that I've worked on a little bit is these direct effects also come up when we're looking at panel data or time series cross-sectional data, and we want to know, say, the effect of a lagged treatment fixing the contemporaneous level of treatment. Or we want to think about what's the effect of an entire treatment history on some outcome. Right, so all of those things are different ways that direct effects kind of are involved, or places where we might see direct effects. So, so there's kind of a key problem that comes up in most settings where we're trying to estimate direct effects, and that's when we take standard approaches. Say we just run a regression with treatment and covariates, and then we add a post-treatment variable, the thing we want to kind of net out. Or we do a matching analysis where we match on that post-treatment variable. Just kind of naively, the problem with these kinds of approaches is that they lead to what's called post-treatment bias. And this can come in a couple different ways, but the worst part of it is that it can lead to kind of a selection bias, because you can induce correlations between treatment and outcome that are non-causal just by conditioning on a post-treatment variable, even if there's no causal effect at all. So these kind of standard regression and matching approaches are not good techniques for estimating these kinds of direct effects. So there have been a whole suite of methods developed that allow you to estimate these direct effects, mostly coming out of the biostatistics and epidemiology literature. And two broad approaches that most people know about are going to be things like structural nested mean models, or generally those kinds of models that focus on modeling the outcome, and also weighting methods. And those are going to be things that focus on modeling the treatment conditional in the mediator, conditional on covariates. Right? So the issue with both of these approaches is that they actually require, especially relative to just a standard approach where you're going to be thinking about just the overall treatment effect, you're going to introduce a lot of potential for model dependence, because both of these approaches are going to require a number of models, at least two, for different components of your data generating process. And just like when we think about kind of running a regression model and trying to estimate a causal effect, right, we're worried a little bit about whether or not the model that we choose or the results that we get are dependent on the particular modeling choices that we make, right, in terms of functional form and other kinds of modeling choices. So this is one key limitation with these kinds of standard methods for estimating direct effects. So the technique the method that we're gonna propose today is going to be this idea we're calling telescope matching, and I'll talk more about why we call it telescope matching a little later. What's nice about this is going to be a consistent method for direct effects, so we're not going to be introducing any kind of post-treatment bias through this method. So it's good. What's nice about it is just like kind of standard matching method that we're used to, it's also going to allow us to guard against the model misspecification and lower the kind of model dependence that we would expect. And the other kind of nice benefit to it is a lot of the logic that we have from the kind of standard matching case and a lot of the intuitions that we have about things kind of carry over and allow us to move in this setting. So here's a kind of,
May I ask a quick question, please? Can you give me a practical example of a post-treatment bias? Like a case kind of post-treatment bias?
Ure. So a kind of standard, a standard example would be something like, if we look at, if you think about the relationship between athletic ability and academic achievement in the population, we might imagine that those things were completely uncorrelated in the population.
Okay.
But if we were to then select on a post-treatment variable, which is admission to a particular college, which is post-treatment to both of those things, we can induce a negative, in fact, you see this, that you can induce a negative correlation between athletic ability and intellectual, like academic achievement by selecting on a post-treatment variable. That kind of same logic is going to carry through to these types of things. But basically, any time that you condition on something that's affected by the treatment, potentially affected by the treatment, you'd be inducing those kinds of selection bias. Okay, so this is just to give you a sense of what I'm going to talk about today. I'll do a little bit of, we'll talk about the difficulty of we'll define and talk about the difficulty of estimating these direct effects with standard methods. I'll introduce our own approach and try to walk you through the logic of it, because it's a little bit more complicated. Even if it's actually just kind of two standard matching steps, some of the logic is a little bit not obvious. So I'll walk you through some examples. I'll show you a simulation that shows kind of if you induce misspecification, how that affects the various estimators that you could use to estimate these direct effects. I'll wrap up. I'll talk about a conclusion and then wrap up with some directions that we're moving in. Okay, and obviously, sorry, but I don't need to say this one, but you can interrupt anytime. So why are direct effects difficult to estimate? So I'm just to kind of start us off with some notation, and I'll give the idea that I'll use some of the application here to think about, to kind of set up and give us something to talk about. So the setting here is going to be a direct effect setting that's been used a couple times in different, mostly mediation papers. But this is going to be an experiment where we're a framing experiment in political science, where we're interested in the effect of either a positive or a negative framing of a news story on immigration, in a particular media accounts of immigration, on things like whether or not a person supports or doesn't support expanding immigration. So here, what people are generally interested in is the treatment is going to be binary, negative frame, positive frame of the immigrants. The mediator in this particular case that the original authors were interested in is various kind of psychological outcomes that might be affected by treatment. Things like anxiety. Right? So it might be the case that this negative or positive framing of immigration might induce higher or lower levels of anxiety in a person, and that might lead them to take different actions or support different policies. Right? And the particular outcome that we're going to be interested in is going to be support for immigration. So A is going to be treatment, M is going to be this mediator, but in general, this is just the post-treatment variable that we want to be able to, net out the effect of, and outcome's going to be Y. And then we'll just kind of define the standard potential outcomes, setting both the treatment and the mediator. So this is going to be the potential or possibly counterfactual level of support for immigration that we would see if this person I had been treatment level A and mediator level little m. Okay. So to some extent, there's a little bit of with some of these things, some of these empirical settings, it may be more or less, when we feel more or less comfortable making assumptions about whether or not you can kind of you could ever directly set these kinds of mediating variables. But in general, we're gonna work with this kind of framework at least to have something to talk about. Okay, so the quantity of interest that I'm going to focus on today is going to be a particular kind of direct effect. There are several, but the one I'm going to focus on today is called the average control direct effect. And that's just going to be the average, the expectation of the individual level direct effects, which are just the difference between what unit I would have had under treatment versus what they would have had under control for a fixed value of the mediator. Let's take the average across all. Yeah.
I have a quick question for you concerning the last slide.
Yeah.
In this model, what kind of confounders are you accounting for?
Oh, I'll get to that.
All right.
Okay, so what we're doing here is we're taking the average of the individual level effect is just the difference between treatment and control for fixed values of mediators, and then we'll take the average of those across the population. So we'll call that tau m, where m is just the level of the media that we want to estimate these at. So we might estimate the effect of negative versus positive frame for, say, m equals high anxiety or m equals low anxiety. Right, so the average effect of manipulating A while holding m fixed to some level little m. So this is generally very easy to identify if A and M are both randomly assigned. Right? If we're in a situation where we just randomly assign some A and some M, then this is, each of these basically equal to the observed average of Y at that level of A and M, and we can just take differences in means and everything is fine. But in many, many, many studies, right, even if A is randomized, a lot of times people are interested in some part of this is going to be observational, either A and M or at least M. So in this particular study, right, the positive and negative frame was randomized, but then this M, the level of anxiety, was not randomized, right? It was just observed in the data, whether or not the people had high or low anxiety. Right? So in order to thinking about estimating this control direct effect in observational studies, we do need to think about things like confounders. And what kinds of confounders do we need to adjust for? In particular, right, this is I'm going to do a causal diagram here to kind of lay out everything so we can all see where we are. We'll think about there being, again, A is treatment, M is affects possibly the mediator and the outcome, and then this kind of red dash line, that's the direct effect of treatment. That's the thing we're interested in. We're going to have a set of baseline covariates. We'll call them X, and those are going to be the things that are pre-treatment and pre-everything, right? They can possibly affect treatment, they can possibly affect mediator, and they can possibly affect the outcome. But importantly, what separates them from another type of confounder that I'll talk about is that they are pre-treatment. They're not affected by the treatment. So these, if we had a simple randomized experiment on A, then there wouldn't be any of these potentially. Right? The second kind of confounder that we're going to be interested in this particular case are going to be what we refer to as intermediate confounders. And these are going to be things that can confound the relationship between the mediator and the outcome, and that are possibly post-treatment. Right, so the effect of A, the A can possibly affect Z, but Z is a confounder for the relationship between M and Y. Right, so we can think there might be a lot of such kinds of things, especially in a study like this, where the relationship between anxiety and support for immigration might have important confounders that are affected also by treatment. So these are going to be the sets, that kind of just notationally, what are the different kinds of confounders, and so what are the assumptions that we're going to have to make in order to do anything and to be able to estimate any kinds of quantities of interest in this case. I'm going to make two kind of fundamental assumptions. The first is going to be what's called sequential ignorability, which it's up here in math, but I think it's much simpler to think about in terms of two separate no omitted variables assumptions, right? Or two separate ignorability assumptions. The first says that given X, the relationship between A and Y is unconfounded, and the relationship between A and M is unconfounded. So it just says that conditional on the baseline covariates, we basically have randomization or as if random on treatment, right? That's the kind of standard selection on observables assumption that we would make if we were trying to do observational data. This might be satisfied generally by if we had an actual randomized experiment. The second assumption is going to be another no omitted variables assumption, essentially that conditional on treatment, baseline, and intermediate covariates, there are no omitted variables for the relationship between M and Y. So in particular, that means that M, conditional on these things, is as if random with respect to Y. right? So we just have this kind of this nested structure such that you just have two kind of standard no omitted variable assumptions in a row. Right? And just the only thing that's changing between these is the conditioning set. Here we just condition on x, and here we're conditioning on ax. Is that clear?
I think it's a more technical point.
Yeah.
So if you look at the first line, how we impose the marginal independence and have one independence?
Yeah, I think that's going to be fine in this case. Yeah, you could do. Yeah, we wrote it as joint, but I think you can do marginal. I'm not 100% sure about that off the top of my head. But I'm pretty sure. Yeah.
So first of all, we get y of a and m, and then m of a, z of a. So does it mean that it's for all m's this is valid, or is it particular m?
Oh, you mean this little m here? Or this one?
Yeah, exactly.
This is saying that these are independent with respect. Yeah, I didn't actually define these terms. I just kind of, so these guys up here are the potential outcomes for m and for z at different levels of a. So these are other kind of these counterfactual quantities that could exist. And what this is saying is basically that the treatment conditional on x is independent of those potential outcomes.
Right. But for all m, for all values of m.
Well, I mean, m is a random variable in this case, so we're not conditioning on m or anything like that. It's just it says that it's independent of that quantity. Okay. Sweet. Okay. The second assumption that we're going to make is a positivity assumption, which just says that conditional for any covariate level that has positive probability. Essentially, we're going to assume that there's a positive probability of observing both levels of A and both levels of M. So essentially, when we think back to the matching literature, that just means that there's basically overlap in the covariate distributions across levels of A for the baseline covariance, and there's overlap across levels of M for all these other variables. So just so these are basically kind of like common support assumptions. Yeah.
I guess if there's a strong effect of the treatment on the median, though, wouldn't that break the second?
It would have to be a perfect effect.
Okay.
It would have to be like there have to be sorting.
But I guess in finite samples, still have.
Yeah. So this is an assumption about like the underlying population probabilities. It definitely could be the case that you have empirical violations of positivity, such that there are empty strata essentially, and there are going to be some. Generally, there are different issues when it comes to this is kind of bad for weighting models. The models that do better for that are going to be generally these kind of structural nested mean models, because they're essentially allow you to smooth across some of these strata using a modeling basically. Here it's going to be tricky. We're going to be okay if there's empirical positivity violations here. Here we can't prune on the second stage or for matching on M, and so we're going to have a little bit of a difficulty. So we can need this to be the case. But essentially, what that's going to mean is there's going to be could be some bad matches. Yeah.
You assume the mediator binary?
Yeah. Here we're going to assume that the mediator is binary. Yeah. Yeah. So because we're going to be thinking about doing matching M's to M's and A's to M equals 1 to M equals 0 and A equals 1 to A equals 0. So it's possible that you could, obviously, like both of those things could be extended if you take on like a kind of a different matching approach. Okay, so the key problem that comes up, so it seems like I've described to you two separate kind of things that would identify two separate like regressions essentially that you could run, and it seems like why shouldn't I just be able to get to like why shouldn't I just be able to include both of these variables? So the problem that comes up when you're trying to estimate this direct effect of A on Y is that if we take a naive regression or matching approach where we regress Y on X, A, and M, right? So that post-treatment variable, we want to control for that. That's like the idea of the kind of intuition. We have two different decisions about what we could do with the Z's, the intermediate covariates. We could omit them, right, on the intuition that they are post-treatment variables, and we shouldn't include post-treatment variables. But when we do that, we're we're going to get omitted variable bias for the relationship between m and y, right? We're omitting an important confounder from the my relationship. You can say, okay, well, maybe I'll control for z, but in that case, you're going to end up with some post-treatment bias by conditioning on something that's possibly affected by the treatment in this case. Right, so well, if we think about a single regression model, where we're trying to estimate, so the basic takeaway from this idea is that from a single matching analysis or a single regression model, unless additional assumptions hold, we're not going to be able to just include m and z here as covariates and read off the coefficient on A as being the direct effect of AI.
And just to refresh my 1920s memories, so suppose you regress y on all the other variables.
Yeah.
And you have the right model.
Yeah.
And then and the coefficients have post-treatment bias.
Yeah.
But suppose you estimate the quantity of interest by physically holding things constant, moving things. Okay, I mean, if that's conditional upon that being the right model, isn't that a perfectly reasonable way of
so if you have so the basic, a lot of these structural nested mean models and stuff like that essentially are ways of doing exactly what you're saying, which is to take the structure of it, put correct models on the outcome, and then basically add up all the paths in the right way to get the kind of right control rate that you're interested in.
So, but isn't this basically path analysis from the 19 whatevers?
So you can under the assumption that the constant treatment effects, yes, they're the same. They're going to basically be the same.
Well, if the model's right, then you have what you're calling constant treatment. If there's
Individual level models, right?
If the model, come on. I mean, back then they didn't think about heterogeneous treatment.
No, yeah.
So they basically just said the model's right, and actually if the coefficient of the area is a function of something else, then stick that in the equation.
Yeah.
Right. So you could actually do it that way, but it would be very model dependent.
Yeah. I mean,
So it's a little unfair from that perspective to say that it's just bias, but it's post-treatment bias. The coefficient is post-treatment bias, because this approach is, it's valid. It's just conditional upon way more assumptions than we're going to introduce.
So I guess what I'm trying to say here is that if you were to take the approach, which is to run a regression of these things on the y on these things, including z or omitting z, or if you match on these things and then do the effect of A, take the difference in means, that if you look at that difference in means, or you look at the coefficient on those things, all of those things will be biased in the direct effect. Right, that's what I'm saying. You're right that there are ways that you could kind of get around this, and like a lot of the other stuff that I've done has kind of been on that, about thinking about how you could use, say, two different regression models. You would basically, the point here is that there's no one regression model that you can run that's going to get you the same answer.
But only if you're obsessed with the idea that the coefficient that comes out of the computer is the quantity of interest.
No, because your model, just to be clear though, but when you're saying like, oh, couldn't I just do path analysis? That's going to require modeling assumptions on other variables here that I have not made.
Yes.
So yes, that's right. Yeah.
Your contribution here is to reduce the number of assumptions, to reduce model dependence.
Yeah.
But not to take a biased estimator and make an unbiased estimator.
No. Okay.
Right.
Okay. Sure. Yeah. I'm just this is
I think
this is the problem. So this is the problem that the literature, that like the biostat literature, kind of like set up and solved with a couple of modeling approaches, and then I will weaken the modeling depends on those methods. So.
I think what you may be trying to say, if I'm correct, is that the more covariates or variables you add into it, the less likelihood for the bias of your estimate in the end. I think that's what it's driving at.
I mean, I think insofar as just on that point exactly. Only insofar as like fewer covariates means fewer modeling decisions, and the hope is that you could possibly make better modeling decisions. But as soon as you have a continuous covariate, you're in the land of making pretty strong modeling assumptions. So I think
it's about modeling assumptions.
Yeah.
I'm not one of the people from the 60s, right? And who are Sewell, right? Who are these people? Right. You pull it, and you tell them all the problems. They say, okay, we got to specify the right model. Once you specify the right model, then you can estimate these things with no problem. And I think your answer is not it's biased. Your answer is that we can do this with way fewer assumptions.
Yeah, sure. That's fine. I'm just trying to set up. This is the standard. This is the standard kind of like trade-off.
Yeah.
To be clear, this is not particular insight. I mean, solving this problem is not unique to this method.
Yeah, sure.
Yeah, that's true.
Well, but I mean, what these guys did was to say that the model's right. So if the model is right.
All models are wrong.
Yeah, well,
They didn't think that way back
not
then.
back then.
All errors are uncorrelated back then.
Well, somebody wrote that in '56 or something, so before that, all models were right.
It's a nice book to live in. Okay, so this is just, I kind of wanted to, this is for people unlike Gary, that are not familiar with this idea about why I can't just include Z or an M in a regression. I just kind of want to highlight this particular issue. So the current approaches that are used that along the lines, the kind of modern versions of the path analysis that Gary is talking about that are used are the problem with them is that they can get you the right answer, but they're generally going to be very dependent on at least a couple of different modeling choices. So in particular, for these structural nested mean models, or this is a part of a broader class of models that are in general trying to use regressions essentially of y on these covariates, the outcome on these covariates in order to identify these effects. They're going to require us to specify some conditional expectation function for y conditional on everything, and then a separate conditional expectation function for y conditional on just x and a. And if the modeling choices, those might be different across those two things due to interactions or due to whatever. But generally, the correctness of this kind of approach is going to depend on the correctness of these kinds of maybe modeling assumptions here. A second broad class of models can possibly allow you to avoid making any kinds of assumptions about the conditional expectation of the outcome, which sounds fantastic, except that here you need to be able to correctly model a different set of conditional probabilities in this case. The conditional probability of the treatment conditional on baseline covariates, and the conditional probability of the mediator conditional on the treatment, and then two sets of covariates. Right, so this kind of inverse probability of treatment weighting, which is a popular approach in biostatistics and epidemiology for things like marginal structural models, these are going to be great, except they allow you to avoid making direct assumptions about the outcome, but you do have to make modeling choices here. And again, the correctness of your model is going to the correctness of your inferences are going to depend on the correctness of your modeling choices here. And there are so-called double robust estimators, which don't really get around this problem either, because all the double robust estimators say is if you can get one of these two sets of modeling assumptions right, then you'll be right. That helps you in the sense that it gives you two shots. But if you have modeling problems on either, it's still going to be a problem. Okay, so what we're going to do is we're going to focus on trying to weaken some of those modeling dependence issues and advocate this idea of what we're calling telescope matching. And this is essentially going to be a two-stage matching procedure. So the way we're going to move backwards from in the causal ordering. Okay, so the first thing we're going to do is that we're going to match across levels of M, using as covariates Z, the intermediate covariates, the treatment, and the baseline covariates. And what we'll do is we'll use those matches to impute a missing counterfactual. Why this is kind of a weird hybrid missing counterfactual, but this is the potential outcome for I under m equals 0 at their observed level of A. And then we'll do a second stage of matching, which is going to match, it's more standard matching, which is going to match across levels of A on the baseline covariates only. Right? So we're going to ignore, in that second stage, we're going to ignore the intermediate covariates. Right? And then we'll use those matches to impute the kind of the basic, the kind of more primal potential outcomes, and use those to estimate the quantities of interest. And it's telescoping here because we're kind of closing the telescope from this step to this step. So right, we have right here we're conditioning on Z and X, and here we're just conditioning on X. So we kind of like close the
So is this still getting like the average control correct effect for the average control direct effect on the treated?
We're gonna focus on here. The quantity of interest. We're gonna focus on the average control direct effect.
Okay.
Yeah. So essentially the real difference between those two is that on the second stage here we're gonna be matching treated to control and control to treated.
Yeah.
So we're gonna do both.
Is this matching with replacement?
Yeah, I'll show you. I'll go through the exact way we're going to do the matching. To some extent, a lot of the choices about how to do the matching are we're going to abstract away from some of those choices, but I'll go through that in a second.
It's related to the question, why only m equals 0, why not?
You can do both. So if you wanted to, you could also if you wanted to. So we're going to focus on estimating the control direct effect at m equals 0, but you could also do it to m equals 1, and you would just kind of flip a lot of the stuff that I'm doing here. The idea is, a lot of times what we're trying to, in many cases, maybe what you're trying to estimate is what would have been, what would have been the treatment effect here if there had been, everyone had kind of a baseline level of the mean here, right? So, if we think of 0 as being some sort of baseline level, that's like a kind of a motivation for it. Yeah.
Well, just a clarification, but do you assume that Z is causally prior to M? Is this something you need to assume?
Z is going to be, Z is going to be causally prior to M. So it's going to be a confounder. Yeah. So if there's something that's post M, you wouldn't need to include it in this at all.
But what if you don't know which one is cause?
Yeah. So that's a general problem with with like the kind of doing mediation analysis or direct effects. I mean, generally, at some point, you need to take a stance on what the causal ordering of these things are. And in general, I mean, we're using this example of the survey experiment. I don't particularly love it, and that's just because I don't like doing causal ordering in people's minds, because trying to figure out what idea or what feeling is causally prior to what other feeling is very difficult. But there's going to be other settings where you can say lag. If you're in a time series cross-sectional setting, you're in a panel data setting, you might be able to lag your covariates in such a way that these assumptions make more sense.
Just clarification. So when you say match M on Z, you're saying
Match.
pick individuals at M equal 1, and then find other individuals for M equals 0, but with the same value on Z and N.
Yeah, I'll go through this in a little more detail. Yeah. But yes, that's essentially it. Yeah. I just want to give a broad overview of the procedure, and then I'll go through them. So I'm going to give you a particular example because this can get somewhat complicated. So here we're going to focus on this as being like an imputation problem with missing data. So each row here is going to be a unit. I have some observed data, A, M, X, and Z, and then I have some potential outcomes that people can take. And this is going to be kind of like the science table, so to speak. So first unit is treated, has M equals 1, X equals 10, Z is equal to 3, and we get to observe this person's potential outcome under treatment. That's just their value of the outcome, but we don't get to observe how they would have responded to other combinations of A. Okay, and then unit 2 here is A equals 1, M equals 0. We get to see them for that column, and then we'll fill this out. So we have 6 units here. I'm going to focus on this example with 6 units. So, and in particular, we're going to I'm going to ignore these other 2 columns for a second because I'm going to be particularly interested in estimating the control direct effect under M equals 0. So these 2 columns are less relevant for us. So basically what I want to do is I want to be able to, the average control direct effect in this case is just the difference between the average difference between these 2 columns. Right? But the problem is we don't fully observe everyone in each one of those columns. Right? We only get to observe the people that actually have those levels of A and M. That's the motivating problem. So what most of these methods are going to do is basically impute where these question marks are using various kinds of methods. Okay, so in our approach, the hard matching approach, the first stage again is going to be, what are we doing? We're trying to find for every we're going to match across levels of M to find good matches. So what I mean is so first thing we're going to do is we're going to subset to a particular level of treatment. So we're just going to, we're going to focus on one level of treatment at a time, right? And then what we'll do is we'll match every M equals 1, so every mediator equals 1, to the closest N equals 0 unit in in terms of x and z. Right, so we'll use some distance metric, Mahalanobis distance, Euclidean distance, or something like that, and we'll find for every n equals 1 unit, we'll find its closest n equals 0. Right, in this case, just in the simple example, we're just going to match it across. Right? And then what we'll do is we'll impute the missing counterfactual for using the matched observation. Right, so if we match y1 to y2, right, then we'll use this kind of like what would have happened to y1 under 0, 0 is approximately what's equal to y2. Right, so we're focusing on the same levels of A. So what we're essentially doing is we're kind of getting, well, that's our best guess about what what y1 would have had under 0, 0 is what we observe for y2. And we can go down the line for each of these. But the important part is that we're finding ones that are close in terms of the baseline and the intermediate factors. Right, and so then we'll create this imputation, which is going to be just the observed value of y when m is equal to 0. Right, for m is equal to 0, we already observe how you would react under m is equal to 0, so we don't need to do anything with you. But if you have n equals 1, right, we're going to find the closest match to you, and we're going to impute your y using that imputation. Right, and I'm going to focus. So in the paper, we don't do one-to-one matching. We do like general matching, but here I'm going to focus on one-to-one matching because it's a lot easier to kind of. There's a lot of notation I don't have to introduce. And I should say yes, this matching is done with replacement. It's not on the slide. Both statements. Okay, so just to give you an example, so here, right, so for unit 1, so again, the first thing we're going to do is we're going to think about, I want to start filling out this column here. Right? So the first thing to do is that we're going to subset to a particular level of A. So I'm going to only focus on just the A equals 1 units right now. And I want to fill in this column for them. And so what I'm going to do is, for the only person I need to impute for this is unit 1. So what I want to do, I want to find the closest unit that does have m equals 0, right, in terms of x and z. And can anyone quickly figure out what unit that is?
Y5 would be matched to both Y2 and 3.
What's that? Say that again?
Y5 would be matched to both Y2 and Y3. Or sorry, are you asking something else?
I'm asking which of the 2 and 3 are closer in terms of x and z to unit 1?
Oh, to unit 1.
Yeah. So that's going to be 2. Right, so basically what we're going to do is, so that means I'm going to impute the missing counterfactual. I don't know what unit 1 would have done under the m equals 0, but what I do know is that it's close to unit 2, and so I'll use them to impute that value. Right, and if we were doing a more general kind of matching, we would take the average of the matches and put it there. Okay. Yeah.
How do you measure being closest, and which level do you prioritize?
Yeah, so there's that. I mean, that's a more general question about matching, and there's all. So when we in the application and things like that, we're not prioritizing. We're doing something like Mahalanobis distance, which is going to try to find matches accounting for the fact that certain covariates are correlated and stuff like that. But in general, I mean, you can prioritize by putting different weights on the different covariates. So if there's a particular variable that you want to be able to match better, you can include that as in that particular way. Okay, so that's how we do that first stage, and then we would do something similar for these guys. Among all of the A equals 0, we would find the missing imputation there. Okay, so that helps us. That at least for within levels of A, we have these columns filled out. And in particular, if we stop there, that would allow us to say get the effect of M. Right. That's just kind of a standard. This is kind of a standard matching for assessing the effect of M, adjusting for X and Z and N. So we're going to go. It's just like we're going to take it to the next step, which is we don't want to know the effect of M. We want to know the effect of treatment, fixing M. So what we're going to do is the second stage of this procedure is going to be kind of a standard matching procedure, but now we're going to use these imputed counterfactuals that we just did in the first stage as the outcome, and we're going to completely ignore M and Z in the second stage. Right, so what do I mean by that? So I'm going to do the following. I'm going to take each control unit and match it to the closest treated unit in terms of their values of x. Right. And then I'll create an imputed value of y1, 0, so treatment m equals 0, which is going to, again, it's either going to use my observed value of the imputation from the first stage, or the imputation for unit j in my match. Right? And I'll do the reverse. So this is getting back to Shom's question. I'll match each treated unit to the closest control unit in terms of x, and do the same, the inverse of that, and get an imputation for the potential outcome under control and n equals 0. And then once I've done that, for every unit, I'll have an imputed value of their level of treatment, the potential outcome under treatment and n equals 0, and control and n equals 0. And I can just take the average, the sample difference in means between these two, or like the standard difference in means between these, to take an estimate of the control archetype. Yes?
If you were to do sort of bias correction here, would you want to do it both stages? So you bias correct your first stage matches, your imputation, and you bias correct your second stage, or would you do it only on the second stage?
We'll do it. Okay. And we'll do it on both. Yeah.
So if you go back to one side, say if the experiment is done, right, then you say
Yeah. If you're running an experiment, then you're basically these you're done.
that one and do there. And then
Yeah. So if A is randomly assigned in the second stage, the second matching stage is that you don't need to do it. That's right. You do need to use these imputed values. Yeah, you do need to use these imputed values, but you don't need to do a further adjustment.
you do the same matching on n in the control group, right?
The same matching on any control group. Yeah. So I didn't show it here, but yeah, you would do.
So you do that and then you just adjust.
Yeah, exactly. Yeah, you can do that. Yeah, I mean, you would just think about it. I mean, you could rewrite it as like a simple matching estimator. But, yeah. Okay, so the second stage we've already kind of imputed here, but now what we want to do is we want to impute across levels of A, right? So we want to fill out the rest of this column. Right, but in particular, the thing I said was important is that we're not going to use any information about M or about Z to do this. So all we're going to do is we're going to try to find for every unit that's in control, we're going to find the closest treated unit just in terms of its x value. So for unit 4, what's the closest unit? So we're trying to impute this value. What's its closest? The closest value that's treated at 3, right? So we'll impute y equals 3 there, right? It's our best guess about what that missing potential outcome is. And then for 5, it's 2, right? And then what's the closest unit for 6? 1. So this is where a bit of the tricky business comes in, which is that we're not going to impute here with the observed value of y for unit 1, but instead we're going to impute with its own imputation from the first stage. Right? Our best guess about what y should have been under control, that's what's going to go down here in the imputation. Right, so we're matching, again, that's how we do that imputation. We'll do that on the second. Over here, we'll do the kind of same procedure. Right, and then we'll just take the difference across the rows and take the average of them, and that'll be our estimate of control. So the thing that's tricky, the one thing that's tricky about this is that where this indirect match, where 2 is indirectly matched to 6 through its first stage match, turns out to be very complicated in terms of doing the asymptotics on this. I'm going to spare you all of that because I had to go through it, and I don't think you should have to go through it as well. But that's one really tricky bit of this, is that the distribution of the large sample distribution of this kind of estimator is going to depend on how often you're matched, but also on how often you're indirectly matched. Yeah.
Is it true in general? So in this case, like units 1 and units 4 aren't used anywhere. Is that true? So, for example, in this case, if something is A11, will it never be used anywhere in the analysis?
Yeah,
because of the x's.
If you're interested in this m equals 0 estimand,
right,
those will never be used. That's right. So if you could also think about doing this for m equals 1, and in fact, in some of the stuff that we've been working on with Tyler is thinking about doing this stuff in terms of doing mediation with this, where you actually do want to do this both ways and then kind of average them together in a smart way. But yeah, when you're focusing here, you're never going to use those units. Yeah.
So for asymptotics, you just write it as a radius, difference in mean.
Yeah, essentially. Well,
So you just do the accounting of how many times.
yeah. So I mean, essentially what we do, essentially what we'll end up doing is writing. I think it's a very similar. I mean, I'll kind of get at that a little bit.
Just intuition.
Yeah, intuition is that we're going to write it as like a weighted average of the y's and think about the differences. Yeah, that's right. Okay, so why do we like this estimator? Well, we think it's simple. There's basically two standard matching steps. So both of the steps that we talked about here involve just basically matching a binary M and a binary A in terms of some covariates. And those are things that that we kind of a lot of us have good intuition about how to do those kinds of matching procedures. One thing that's nice, if you think that this is a problem, is that both steps of the matching can be done. So you can actually find the matches for A and the matches for M without access to the outcome data, right? Because there's nothing about I was kind of showing you this. Oh, I compute things in this way, but there's nothing about the actual values of Y that influence either the first or the second stage, right? So you can actually figure out the identity of the matches first, and then get the data later. So you can think you could do this before you get the outcome data, or you could do this. You could do this in some sense, tying your own hands so you're not going to be hacking. This is going to be, so we do an analysis similar to body and bins, and this is the kind of roughly the same style of kind of how we're going to try to do this. And we can show that this is a consistent estimator for the control direct effect under some regularity conditions. It's unfortunately a bias estimator, and Max was doing this a little earlier. So the problem with this is, even though it's consistent, it is biased, and that may not be a problem typically, right? But unfortunately, with these matching estimators, is that that bias converges to zero very slowly, right? And so what that ends up doing is that it means that for a lot of these matching estimators, and this is no different, it basically it doesn't converge to a normal at the rate that you would want, right? And so things like you could get kind of either asymptotic bias, or you could get things where the standard errors are just not accurate. And so what we do in the paper is we develop a bias correction technique to get around this, and that happens in 2 stages. And finally, I'll show you in a sec, is that these are going to be more robust to modeling specification. Yeah.
Can you talk a little more about the bias and why does it not? What do you want to be doing?
I'm not going to talk about why the bias converges slowly, but essentially the problem is that, I mean, if you think about it, if you're taking a fixed number of matches and you're letting the data grow, you're never going to get. There's always going to be matching discrepancy between a particular set of matches, and if you're never allowing the number of matches to grow with the sample size, you're basically that there's going to be that fixed amount of matching discrepancy that always exists. If you allow the number of matches to grow with the sample size, this doesn't become a problem. And so there's a little bit of like, how big of a problem is this? It's like if you tune things, maybe it's fine. But just like under these assumptions about the way you do the asymptotic system. So it's not clear that this is always going to be a problem, but it could be. So I was going to talk really briefly about the bias correction that we do. And so one other way that you could think about doing these kinds of estimating these kinds of effects is, instead of doing this kind of matching imputation, you could do a regression imputation. Right, so instead of, say, filling in that value with some matched value, you could fill it in by running some regression of Y on X, Z, A, and M, or among units with M equals 0. So just among, these guys here, or I guess these guys. And then you would develop a regression model. You would get predicted values for this particular unit, and you would fill that in. Right, and if you did that, you could do that for all these different values and take the difference in means, and that would get you an estimate of the average control effect. Right. It's a little bit. This is essentially what a complicated version of this is what structural nested mean models are doing. Okay. So what we're going to do is we're going to use that idea that there's this kind of regression adjustment imputation you could do to get a bias correction procedure. And so we're going to use regression to adjust for the imputations for the matching discrepancies that we see. That we observe, right? So there are no perfect matches, essentially, as soon as you have a continuous covariate. And so you're going to end up with some matching discrepancy. So what we're going to do is that for the first stage, we're going to basically bias adjust on both stages, bias correct. So we're going to take, the kind of imputation that we're going to use is going to be a combination of the matched unit, and then the difference Right, so that's the raw outcome from the match unit. And then the difference in the regression function between the unit that we're trying to match and its match. Right, so the idea there is we're using regression to figure out kind of how much actual bias is there, how much matching discrepancy is there in terms of the conditional expectation function. And we're going to add that bias, to kind of add our estimated bias to the estimate, and that's going to kind of take away the bias from the outcome. So it's going to give us an imputed value. And then the second stage, what we'll do is we'll just use this new imputation, which is supposed to be bias corrected, as the outcome in the second stage, where we again use the raw match that we had from the first time, in the kind of the way I've been developing it so far. And then the second regression is going to be taking this first stage bias corrected outcome and bias correcting it. So this would be essentially kind of like what I've worked on in the past is called sequential G-estimation, which is just regressing that the demediated function or the blip down function or the y, use that as the outcome, and that's going to get you a sense of how much bias there is on that.
If you were able to exactly match everything.
Yeah. If you were able to exactly match everything, you wouldn't need to do this.
Right. So all Abadi and Emmons are saying, and therefore what you're saying in this specialized version is, don't just take the difference in means, run a regression.
You need to run a specific regression. I mean, the problem with that is that you're going to end up with that's going to be biased for the same reasons that regression is always biased for the average treatment effect. So if you're willing to handle a kind of like a variance weighted estimand, then yes. But if you want to actually get like you want to estimate the average control direct effect, you would need to do something like.
So you're basically in the situation of having imbalance left.
Yeah.
And then when there's imbalance left, you have to deal with it.
Yeah.
And so one way is, like I was saying before, you just assume that if the model's correct,
Yeah.
you're fine. Another way is you could estimate the average, but pay attention to various kinds of robust estimators.
Yeah, I think if you assume that there was no interaction between A and M, essentially I think that would be exactly what this kind of first stage would get you. It's less clear to me how it works in the second stage, the kind of straightforward, just like run. You might be right that it's just like run sequential G-estimation on a matched sample, make it over.
So in practice, you don't have enough observation, right? Not much units.
Yeah.
You end up like fitting a global regression.
Oh yeah. So you're not running like these on just these two. Is that what you mean?
Oh, okay. I wasn't sure what.
Yeah. Sorry. This is basically you're gonna run. This is a regression of y. It's like y on x, z, and a for among just the m equals 0 units, and you can also do it among just the a equals. Yeah. So I think you would run. I think in practice, what you end up doing is you run 4 separate regression models, one for each level of the different
Right.
AM
So the
combinations.
assumption essentially is that after matching the regression function is correct.
Yeah, essentially, in order for the consistency to work, you're going to need for these things to be consistent. The hope is,
Right.
with all of these things, that because it only depends on the estimation function through the difference between the matches within match units, that is not going to, that these discrepancies are going to be small.
Right.
Modeling the specification here is going to be smaller. I mean, that's essentially a formalization of the point that you guys made in the matching paper, which is that, once you're doing this within matches, the kind of whatever mistakes you make in terms of modeling are probably small.
So this bias adjustment can be done like even without matching.
Yeah.
Basically fit the model and then use the say treated group X to predict the Y of 0.
Yeah. So that would be essentially what it's been proposed in a lot of different ways, but that's what Imbens proposes in his review.
Yeah.
And if you did it twice like this, it would basically be sequential G-estimation.
Right.
And so we show in the paper that there's that kind of
You
relationship.
should just instead of another two.
Yeah. Exactly. Yeah.
Okay.
How much does it make a difference? I'm just curious.
The bias correction?
Yeah, like the second stage is more important or the.
We haven't done as much testing about the raw versus the bias corrected. We were finding just because of the number of just raw, there's like my recollection of it is that we moved away from it very quickly because it was we were getting pretty poor, especially standard error performance on efficiency. So, and you'll see in the empirical examples, the standard error scan will quite good relative to standard. Yeah.
Just looking at the scale of y here. So if y is a binary, and then you start correcting for the bias, you sort of taking away now the probability from that from the binary. How does that sort of affect the estimation?
Yeah. So generally these kinds of deviation or like look down things, structural nested mean models, are not great for binary outcomes. And I don't think there's not a single like agreed upon approach. There's a lot of like there's no great structural nested mean model or structural nested model that will say bound within a 0-1 interval in a way that's like super appealing. So essentially what you're going to be making is kind of like some linear probability assumptions. Which again, hopefully the idea is that that's not going to matter a lot because it's mostly going to influence things through the discrepancies, which are going to be hopefully like in this like close in the data and also not you're not going to be extrapolating too far out. So yeah.
Sorry again about this. I didn't quite understand. So you have 3 values. You have y of L, and you have 2 empirical using regression. One is for I itself, and one is for L.
Yeah.
So you have 3 values, and you want to estimate 1 value using these 3 values.
So sorry, no, this is sorry. I should say these are predicted values. So I should be more clear. This is the predicted value of this regression function for unit I, basically, and this is the predicted value of the same regression function for this at the value of L.
Yes. My question is this the unique linear combination that gives you an expected value of the estimation of y tilde I? Because what I mean, why this?
Because this is an approximation. This is an estimation or approximation of the bias that we have from the matching discrepancies between these two units.
Is this unique?
What do you mean by
I mean, there might be other linear combinations that will give you an expectation of the same thing.
Possibly. I don't. Yes, there may be other. So in a very limited sense, yes, it could be the case that there are other ways to estimate the bias that could be better, or it could be different. I'm not saying this is unique as some of the other biases. So just the variance of this estimator. So I just talked about kind of bias and consistency and stuff. The variance of this estimator is really complicated. It's just true for a lot of these kind of in this kind of like framework of the asymptotics that we did in the paper. And that's basically because each I can be matched multiple times at each stage. And so this tau hat is not just a sum of IID random variables. So you can't just like pull out your standard central limit theorems in order to get things out. And so there's a couple of different ways you can think about this. Well, one, the kind of standard thing to do if you're in a situation is where that's the case is you just do a non-parametric bootstrap. But in a paper about the image show that this can naively resampling rows is invalid for matching estimators. And this has to do with preserving the distribution of how many times a matched unit is in the sample. And basically, when you have a unit that's included in the bootstrap twice, they get doubly matched, potentially, right? And so that distribution gets a little skewed. How much this is an actual problem in actual data seems really up for debate. In fact, when we first started doing this, we were just doing naive bootstrapping, and we found it to be fine.
Yeah.
But
I never see any examples that fail.
yeah. So what we do, but being good, diligent little workers, what we went and so what we can do here is we can use this this approach by Otsu and Rai and Jazz in 2017, which is they call a weighted bootstrap, which essentially, what I said here is that this is a sum of not IID variables. It's essentially a unit-specific weight to each unit. As long as you can linearize the estimator, you can do this kind of way. You resample both the units and their weights, their contributions to the estimator. You resample those things, and that'll give you a decent coverage. But like I said, in actual practice, we find these things. Okay, so let me show you some simulations, and then I'll show you some actual application, and then we can. So in this particular example, I'm gonna this is the DAG that we're gonna do. So we're gonna have two baseline covariates, one intermediate covariate, and then an unobserved variable u. So in this case, notice that even though that u is unobserved here, sequential ignorability holds because conditional on z, m and y are unconfounded. Right, so we're just basically, that's what's nice about this example is that it's very easy to set up in the sense that that we're going to have a very easy true control direct effect, which is 0. So you can see there's no arrow here from a to y. That doesn't go through m or z. And the delta here is going to control the magnitude of the post-treatment confounding. So it's going to, how much how much confounding there is between m and y due to z is going to be controlled through this delta, basically, through the relationship of the unmeasured confounder on z. When z is not equal to 0, controlling for z in a naive regression will include induce post-treatment. Okay, and then so in order to think about misspecification, we're going to take an approach that's similar to what Kang and Schaefer do in their paper. But in general, what we're going to do is we're going to create versions of the covariates that are like functional form differences between them. So for x1, we'll just take this exponentiated and divide by 2, right? X2 and z. So we'll have these kind of nonlinear functions of the true covariates. And we'll assume that our analyst only has access to these variables, not to the underlying true covariates. Right? So that's a way to kind of simulate or mimic what is the fact that we don't actually know, we didn't know this, how would these estimators do? And so the comparison methods we'll do is we'll do a naive regression that conditions on everything. And then we'll do a sequential G-estimation, which is just structural nested mean models with linear conditional expectation functions. And then we'll do this telescope matching with bias correction. And we'll do the number of matches we'll use in this is going to be just 3 at both stages. We have not thought a lot about it. It's very difficult to do the analysis about how the number of matches affects things, and in particular how at the different stages it might affect things. Okay, so on bias, so here is on the x-axis here, what we're looking at is on these 2 panels is going to be the amount of post-treatment confounding. Right, so this is how much is m actually confounded by z. And the 2 panels are going to be on the left is the correct specification, on the y is the incorrect specification, where we don't have access to the true covariates, and the vertical axis is going to be the absolute bias. And what you can see is the first here is that this is just a linear regression with everything included. And in the correct specification, when there's no post-treatment confounding, the linear regression does really well. Basically, you're unbiased, fine. But as I increase the amount of post-treatment confounding, I see that this is getting worse and worse. We see a similar pattern in the incorrect specification, but it's just that the amount of bias that exists when there's no post-treatment confounding is high because this is modeled misspecification. We've included these covariates naively without adjusting for them in the right way, right? Because we don't know the true function. Okay, when we use sequential G-estimation, we have this nice thing where as I increase the amount of post-treatment confounding, right, this is the kind of standard thing where we're doing this in a kind of estimating the control direct effect in a smart way, and we don't see any bias as we increase the amount of post-treatment confounding because that's the whole point of structural nested mean models. But we can see that we still don't see any change as a function of post-treatment confounding in the incorrect specification, but we see a big jump up in terms of the amount of bias there is. Right, for telescope matching, what we're seeing here is 2 things. One, we basically, in terms of bias, recover something very similar to what the sequential G-estimation gets. But nicely, in the incorrect specification, we're seeing a much lower level of bias when we have the incorrect specification, which is this idea that we're guarding against at least some of these kinds of model misspecification issues that are going to arise in both linear regression and sequential G-estimation. Right, so I think, Gary, you're right. This difference is the real contribution of the paper, not the difference between the red and the green models. Yeah, next.
What's the intuition for why the bias gets better as you have more confounding?
We do not have a great intuition for that. Obviously it's probably just a feature of this particular design setup.
Do you think that's like generally true?
No, I don't think so. It's probably just the case that it's just the way the bias is going in this particular case just means that that's the direction. And if we look at this with the root mean square error instead of the bias, what we see is the kind of the exact thing that we would kind of expect to see. We see that, you know, even though in terms of bias, right, telescope matching and sequential G-estimation look basically the same. When we look at the root mean square error, there's a penalty here for when the assumptions of the sequential G-estimation are correct, right? Matching is less efficient than the equivalent simulation for sequential G-estimation. But again, that is dwarfed by what happens if we have incorrect specification with bias due to model the specification. Right. So yes.
In the incorrect specification case, the bias tends to matching pretty large in terms of magnitude.
Here?
Yeah.
Yeah. Yeah. So part of this is going to be the fact that
Maybe imperfect matching.
yeah, this is due to imperfect matching and imperfect. And again, so one thing just to note, here we're using this is technically incorrectly specified, right? Because we're doing bias correction here, but we're doing bias correction with the wrong covariates.
So maybe the bias actually comes from incorrect correction.
Yeah. Still think we see bias on the matching discrepancies. We should compare it to see what just raw matching would be, but we don't. But yeah, you're still going to see, you know, here. I mean, this is not we're not in a world where actually the assumptions hold. This is a world where we don't have access to the true regression function. So, but we still get correction. Okay, so just really quickly on this application. So this is a paper by Brady, Sue, and Valentino, and this is the effect of media messages, frame on media messages for support for immigration. So the main story in this paper is that if we have a negative tone media count plus a non-white immigrant, that's the like one of the frames, that seems to have reduced support for immigration. So this is when you portray non-white people in a negative light, white people tend to reduce their support for immigration, which is not insanely shocking result. So the question is that they were interested in the paper, and that we're going to think about today is that treatment also affected levels of anxiety, which we're going to think is the mediator. And so the question that control direct effect would answer is there an effective treatment that remains even if we were to hold fixed the level of anxiety? Okay. So you can do mediation in this particular example, but we may think that the kind of mediation assumptions, which I didn't really talk about today, but that essentially assume that there are no these intermediate covariates. Z generally is not there, or that we're going to kind of model them as, or we're going to think about them as multiple mediators and then put them as part of a big overall kind of estimation strategy. But in the kind of standard mediation case where you want to know what is the mediation effect, or the kind of the indirect effect through anxiety, you have to assume none of these post-treatment confounders. And that might be suspect in this case because we might think that there are other things that are affected by treatment that could confound the relationship between anxiety and support for immigration. So what we'll do in this particular example, and this kind of is getting back to like, we're just going to assume a causal ordering and then we're going to go with it. So we're going to take pre-treatment confounders here as education, gender, income, and age. And then the post-treatment confounder that we're going to use, again, you could argue about whether or not this is a post-treatment confounder, is, at least this was measured around the same time, is a perceived harm due to immigration. So this is asked after the treatment. And so this is something that could be potentially affected by it. So if you look at the average treatment effect here, we can see that that there's a positive, I guess the way this is going is a positive frame is leading to more support for immigration. That's the direction here, in terms of the average treatment effect. When we do a naive regression, that can just include Z and M, the anxiety and perceived harm. The coefficient for the treatment goes down a little bit and gets kind of, borderline significant. And if we do sequential G estimation, we actually recover something that looks very similar. And all three of these estimates are kind of maybe in the same ballpark. And all of these kind of suggest that the control direct effect is positive. So even if after kind of fixing the level of anxiety, there's still an additional effect of this media frame, which suggests that there's something else going on left in the data. But when we do telescope matching, and now you're starting to see some of that trade-off that exists here, we see that we get an estimated effect that's much closer to 0, making it a much higher uncertainty. It makes it difficult to reach a lot of conclusions, but if you were to just take a point estimate here, you would say that fixing the mediator is eliminating most of the treatment, but you have a large degree of uncertainty. Right, so this, here in this particular case, this is another way to think about this from a more methodological standpoint is that this is the cost of weakening some of the assumptions, the kind of the modeling assumptions you have to make, and we may not be able to make many inferences if these assumptions are not true. Okay. So just to wrap up, so standard matching doesn't work for direct effects. Direct effects models such as sectional mean models and IPTW or model dependent. And so we introduce this matching procedure to kind of close this gap, to kind of bring another set of a toolkit to the direct effects estimation literature that will kind of help. So it's biased, we use bias correction, and we use weighted bootstraps. So the things that we're thinking about doing next are kind of, we do have some undercoverage in smaller samples, and we'd like to think about better estimators for that. So the thing we're working on with Tyler is to think about applying the idea of mediation analysis when there are no intermediate covariates, and that assumption does hold. Can you use this kind of matching technology in order to do things there? And how to handle dropping units in the first stage. Because if you do drop units in the first stage, you're actually inducing the tricky effects. So you can't do pruning, at least in the first stage. So it's like an optimization. So that's it. That's all I have.
That's all we have time for, but feel free to come up for questions. Thank you.
Is there a way you could do sort of like Houseman type idea to figure out whether